So in that, the contents of the DC and AC bridges are Wheatstone bridge, Kelvin bridge, and AC bridges are measurement of inductance, measurement of capacitance, and Wien bridge. So these are the various types of DC bridges and AC bridges. So let us discuss about the one by one concept. So first, why a bridge circuit? So why we have to use the bridge circuit? The first point is it is used for precise measurements of resistance or reactive components or impedances, temperature, pressure, strain, and other physical quantities. And second point is present in many expensive real-time monitoring devices where physical quantities are measured. And bridges also used to rectify AC signals and filters and oscillators. So these are the main purpose for used in the bridge circuit. And the bridges are not only used for the measurement of resistance, but it is also used for the measurement of various component values. So bridge is not only used for measurement of resistance value, it can be used for measurement of capacitance and inductance. And the bridge circuit in its simplest form consisting of network of four resistive arms and it forming a closed circuit with DC source applied to opposite junctions, and the current detector is connected to other two junctions. So the opposite of one junction is connecting one source and other junction is we are connecting to current detector. And mainly the bridge circuits are used for comparison measurement methods. So mainly it is used for comparison measurement method and it operates on null detection principle. So mainly the principle of or it operates on the principle is null indication principle. So by using these bridges, it can compare the unknown values with known values. From that we can calculate the unknown value. So it can comparing the values of unknown components that of an accurately known component. So from that we can easily to calculate the known value. So by comparing with unknown value. So in that bridges are divided into two types. One is balancing bridge and another one is unbalancing bridge. So when we can say balancing and when we can say unbalancing. So in a bridge circuit, when no current flows, so in a bridge circuit, when no current flows through the null detector, which is a galvanometer. So that null detector is also known as galvanometer. That bridge is said to be balanced. So in a bridge circuit, when no current flows through the null detector, which is a galvanometer, the bridge is said to be balanced. So that relationship between the component values of four arms at balancing is called balancing condition. So that balancing condition is called when components of the four arms of bridge is balancing. So from that we can calculate the unknown values. So the first one, the basic DC bridge used for the accurate method for the calculation of resistance. So the first DC bridge is Wheatstone bridge. By using that Wheatstone bridge, we can calculate the resistance value, accurate resistance value. So in that, so the bridge circuit is divided into two types, DC bridge and AC bridge. So in that DC bridge resistance, so in that Wheatstone bridge, by using the Wheatstone bridge, we can calculate the resistance, and Kelvin bridge we can calculate the resistance, mega ohm bridge we can calculate the resistance. And coming to the AC bridge, so in that can be divided into three components. One is inductance, capacitance, frequency. So by using the AC bridge, we can calculate the inductance value, we can calculate the capacitance value, we can calculate the frequency value. So under inductance, Maxwell's bridge, Hayes bridge, Owen bridge, and etc. And coming to the capacitance, under capacitance shearing bridge, and coming to the frequency, under frequency Wien bridge. So these are the different types of AC bridges under inductance, capacitance, and frequency. So now coming to the first one, DC bridge. So in that DC bridge, the first one is Wheatstone bridge. So what is the purpose of Wheatstone bridge? We can calculate the unknown resistance value. So we are already said the bridge is consisting of 4 resistive ratio arms. So in that, this R1 resistance 1 arm, and second arm consisting of R2 resistance, and third arm consisting of R3 resistance, that is variable resistance. This arrow indicates the variable resistance, and the fourth arm consisting of fourth resistance. So in the two opposite arms connecting null detector, and the two opposite arms are connecting switch position with battery voltage. So when the circuit is on, then the switch is in closed condition. Suppose if the bridge is not in on position, then or in working position, not in working position, the switch is open circuit. So coming to that, when the switch is closed, so when the switch is closed position, current flows. So the current will be entering into this direction. So into 2 ohms. At this point, the current is divided into I1 and I2. So initially, the current capital I is flows here. At A terminal point, it is divided into I1 and I2. Next, the bridge is balanced when there is no current through the galvanometer. So we are already know the balancing condition. What is that balancing condition? The bridge is balanced when there is no current through the galvanometer. So at this galvanometer there is no current passing, or when the potential difference at C point and D is equal. So when the galvanometer current is 0, suppose if the current does not passing through the galvanometer, that current is equal to 0. At that condition, the potential at C terminal point is equal to potential at D terminal point. So therefore, according to that, I1 into R1 is equal to I2 into R2. So this I1 current passing through the resistance R1, I2 current passing through the resistance R2. This equation we can consider as first. And for the galvanometer current to be 0, what we can call galvanometer current to be 0. So at that condition, whatever the current passing through the R1 resistance, the same current passing through the R3 resistance, since the galvanometer current is 0. And same similarly, whatever the current passing through the resistance R2, or whatever the current at A to D terminal is equal to the same current at B to D terminal, since the galvanometer current is equal to 0. So therefore I1 is equal to I3 is equal to, so when A to C and C to B, so when A is the one terminal point and B is the another terminal point. At this, what is the voltage? Capital V. So that is equal to V divided by, for this point to this point, the total voltage is V divided by R1 and R3. So when you are observing the circuit diagram, this R1 and R3 act as a series circuit. So V divided by R1 plus R3. And the same thing at A to B terminal point, the same voltage, the resistance R2 and R4 act as a series circuit. Therefore, I2 is equal to I4 is equal to V divided by R2 plus R4. So now after substituting these two values, that means we are already knowing that, so I1 into R1 is equal to I2 into R2. So that I1 is equal to I3 is equal to V by R1 plus R3, V by R2 plus R4. So after that simplifying this equation, then the equation we can get the R4 is equal to R2 R3 by R1. So this is the equation for the bridge to be balanced. So once the bridge is balancing condition, then the balancing equation is R1 R4 is equal to R2 R3. This is the Wheatstone bridge. Suppose if this resistance is unknown resistance, then Rx is equal to R2 R3 by R1. So by comparing the unknown value with the known value, we can calculate the unknown values. So next step. In that second one, sensitivity of Wheatstone bridge. So up to now we have discussed the balancing condition. Suppose if the bridge is unbalanced. So when the bridge is in an unbalancing condition, then the current flows through the galvanometer. Suppose if the bridge is balancing means current does not flow through the galvanometer. Suppose if the bridge is unbalanced condition, then current flows through the galvanometer. Once the current passes through the galvanometer, it causes the deflection. So that deflection we have to calculate. So how we can calculate the deflection means deflection is equal to sensitivity to current. So where S is the sensitivity and I is the current. So now we can see unbalanced Wheatstone bridge. So in the previous one is balanced Wheatstone bridge. Now unbalanced Wheatstone bridge. See that unbalanced Wheatstone bridge. So now we can comparing with the balanced Wheatstone bridge and unbalanced Wheatstone bridge. In the previous balancing, here there is a galvanometer, but now there is no galvanometer. So that means in the previous the galvanometer current is 0, but here the galvanometer current passes through. So this much of current value we have to calculate how much of current passing. Suppose if the current does not passes means no need to calculate. Suppose if the current is passing means we have to calculate how much of current passing through that galvanometer. So if the current is passing means unbalanced Wheatstone bridge. If the current does not passing means balanced Wheatstone bridge. So how we can calculate that deflection? So to determine the amount of deflection that would result for a particular degree of unbalance. So first determine the current through the galvanometer. How we can calculate the current value through the galvanometer? The first condition is to find the Thevenin's equivalent as seen by the galvanometer. So according to this circuit, we have to convert into Thevenin's equivalent circuit. So how we can converting the Thevenin's equivalent circuit means disconnecting the galvanometer from the bridge circuit, we can find the Thevenin's voltage. First we can remove the galvanometer and then we can converting into Thevenin's circuit. From that we can calculate the Thevenin's voltage and then to determine the open circuit voltage between A to B terminal. So see that applying voltage divider rule equation, then we can calculate the A to B terminal. What is the voltage divider rule? Wherever we are calculating the voltage, that particular resistance divided by total resistance into voltage. So now you can see that now we have to calculate at A terminal point voltage. So A terminal point voltage is equal to what is the total voltage for this? B, and the resistance R3 divided by these two are connected in series position. And same similarly at B terminal point R4 divided by R2 plus R4 the same voltage. So from that we can difference between the A and B. So VA minus VB, that is the V Thevenin voltage. So after substituting we can get the values. Next, Thevenin's equivalent resistance. So in the previous we have to calculate only Thevenin's voltage. Now we can converting into Thevenin's resistance. How we can calculate Thevenin's resistance means the Thevenin's equivalent resistance can be determined by replacing the voltage source with internal impedance. So just we are replacing the voltage source with its internal impedance. Otherwise short circuited and calculating the resistance looking into terminals A and B. So just you can replace this only purely resistance. So according to the circuit, how it is connected, whether it is series or parallel or series. So from that we can calculate the Thevenin's equivalent resistance. So first we can observe this. These two are connected in parallel position and these two are connected in parallel position and those are connected in series position. So like that R1 parallel R3, R2 parallel R4, those two are connected in series position, that is addition. So R Thevenin is equal to R1 R3 by R1 plus R3, R2 R4 by R2 plus R4. So now if the galvanometer is connected across A and B terminal, then how much of current? So that is Ig is equal to V Thevenin by R Thevenin plus Rg, because I is equal to V by R. So V Thevenin is the voltage and R Thevenin is plus Rg, that galvanometer internal resistance. So from this we can calculate the unbalanced Wheatstone bridge.